The next family of reactions that we're going to look at in this unit do not have an opposite per se. They're a little bit of a standalone, and they are called single displacement reactions, sometimes also called single replacement reactions. So let's go back to our family analogy or our people analogy for chemical reactions. Again, where we have yellow and blue characters representing metals and the red and the green representing non-metal elements. The good news about single displacement reactions is that there are only two scenarios to consider as opposed to the many multiples of examples that we had in synthesis and decomposition. So in the first scenario, we have a metal element here. And the metal element is all by itself. And over here, we have a metal bonded to a non-metal. In other words, we have an ionic compound. And the analogy we can use here is a little bit like being at a social function, like a dance, where blue and red are a couple that are dancing together, with yellow being a person who would like to cut in and take the place of the gender that is the same as him in this case. So the metal can only come in and say, hey metal, I'd like to try and bump you out. And if that metal is powerful enough to bump out the metal that's already in the ionic compound, that switch can happen. And we'll talk about how we know whether it's more powerful or not a few slides in from here. From a chemistry standpoint, though, yellow is neutral because it's simply a metal element, but the metal that's in the ionic compound has some sort of positive cationic charge. And so in order for them to switch places too, they must also resume each other's charges. So the metal can lose electrons and in doing so becomes positively charged in order to be able to dance with red. And blue, being positive in order to become neutral, must gain those electrons in order to become neutral in neutral spot. So when you have this switch take place, you would have then as products blue out on his own, and you would have yellow, if yellow is powerful enough, taking the place of blue and dancing with red. And so on this side of the equation, you end up with a metal element, which is different from where you started, and you end up with a metal bonded to a non-metal, or a new ionic compound. So the other scenario is similar in that that one bumping can occur. In this case, instead of focusing on the gentlemen or the metals in this scenario, we're going to look at some non-metals. So let's assume that red is a non-metal element, and so is green. And yellow is a metal element, and non-metal is interested in taking the other non-metal spot and dancing with yellow. But in order to do so, non-metal red has to gain some electrons because the non-metal here in the ionic compound will have a negative charge, and non-metal, in order to become neutral, must lose those electrons to go out here to where red was. And again, it depends on whether red is strong enough to actually overtake green and take that dance position, if you will. So the switch ends up looking like this. We have green out by herself and yellow and red dancing together, forming a new ionic compound because the cation has changed, and we have a new neutral non-metal standing out here. So those are the two scenarios in which case an element can take out its similar type of element in an ionic compound, but there's also a charge change that must take place as well that unfortunately our little family scenario can't quite illustrate. But in order to be able to illustrate it, let's go straight to some examples. So in single displacement reactions, one element can bump out another element from an ionic compound, but they must be the same. Only metals can bump out metal cations, non-metals can bump out non-metal anions, and there is a bumping hierarchy to consider that we'll get into in a little bit. But for now, let's look at an example and going from words to chemical equation to structural equation to see what this might look like. So we take copper as a metal element and react it with silver nitrate, which is an ionic compound. We notice that the products of the reaction are elemental silver, which is neutral, and copper 2 nitrate, which is ionic. And so you can see that copper takes silver's place and bumps silver out to be on its own. If we convert that word equation into a chemical equation, it would look like this. And over here, we have nitrate taken twice with copper because it's copper 2 nitrate, and nitrate's charge is only 1 minus, whereas copper, having that Roman numeral 2, implies that it has a 2 plus charge over here. So it doesn't matter that over here there was a 1 plus and a 1 minus together. We now have to consider balancing the equation. So how do we do that? Well, we might consider maybe going to some sort of cloning type of thing. Looks like we're missing a copper here, so we're just going to put that in. Okay. Pardon me. So the first thing I look at when I see this equation is everything is balanced except for nitrate. So why don't we balance the nitrates first? On the right-hand side, there are 2 nitrates, and on the left side, there are only 1. So let's clone this and create 2 of them. In doing so, however, there are now 2 silver elements on the left, and we only have 1 on the right, and so we need to clone it as well. And when we're balancing equations, we're not balancing the fact that we have silver ions and silver atoms, we're just balancing the fact that we have silver on both sides. And now we have a balanced equation. So it took 1 copper with 2 silver nitrates to produce 2 silvers and 1 copper 2 nitrate. Let's look at another example of a bumping scenario. And I chose this one because in this unit, we're going to find that writing out water as HOH helps us a little bit in terms of predicting products rather than writing it as H2O. So sodium reacts with water, we saw this in class, to produce hydrogen gas and sodium hydroxide. And hydrogen, of course, is part of Hofbrinkel, or that group of diatomic elements we have to always remember are written as partners of themselves and not as singles. So I have the structural equation there. Or sorry, I put the structural equation up first and I have the chemical equation below. And I'm wondering if we can balance the equation by inspection, the chemical one, rather than doing the cloning. So let's see if we can. Talking it out, I noticed that I have 1 sodium on the left and 1 sodium on the right, so far so good. And then I noticed that I can sort of balance this by hydrogens or by H's and OH's. So I notice here that I have 1 H plus, if you will, and over here I have 2 H's, but I also have 1 hydroxide and 1 hydroxide. So it's the H's, or the H portion, that's out of whack. So I'm going to need to double it in order to make there be 2 H's to balance with the H2 over here. However, in doing so, I have doubled the hydroxides, and so let's double the hydroxides by putting a 2 in front of NaOH. Now I've doubled the sodiums in that process, so I can go back here and I can double the sodiums, and lo and behold, the chemical equation ends up being balanced. So when you look at the bumping in this one, we notice that sodium is a metal, and in the case of water, hydrogen is a metal too. And sodium comes in and takes hydrogen's place. Hydrogen can come back out. Sodium has to lose an electron in order to become Na+, and H up above has to gain an electron in order to become neutral H. But it took 2 of each of those so that we can end up with H2 being the product instead of just plain old H. And that's necessary because hydrogen is, in fact, as I said earlier, a diatomic. All right, let's talk about this hierarchy that was alluded to on a slide. When you get a chance to in class, or you can Google it as well because it's data that you can find on the internet as well. I'd like you to look up something called the activity series of metals. In class, it's on page 165 of our Nelson Chemistry 11 textbook, and I actually want you to copy it onto your periodic table. I mentioned in class I don't ever want you to mark up that periodic table or add any extra little hints or tricks or anything like that. But in this case, I do want you to copy it, and that way I don't have to include it on tests and I don't have to include it on the exam. You'll have it with you all the time. Now, basically what this activity series does is it allows us to see what bumps out what. And so it's kind of like a poker hand. There are different metals that are a little bit more powerful than other types of metals. And because you likely don't have the textbook in front of you right now, I will give you a little bit of an idea as to what that looks like. So the activity series starts with lithium at the very, very top. It is the king of all things. It can bump out absolutely positively anything else. At the very, very bottom, the weakest of the metals, Au, is gold. It is not able to bump out anything at all, or if it does so, it's an incredibly, incredibly slow reaction. And so you can notice that a lot of group 1 and 2 elements are sort of at the top of this list. We have lithium as an alkali, potassium and sodium. We saw that those reactions are very vigorous in class. They react with water quite readily. We see barium, calcium, magnesium as alkaline metals are all near the top as well. And then we get into aluminum and some of the transition metals, zinc to iron to nickel to tin, lead, hydrogen, copper, silver, and gold. So the way that we use this hierarchy is this. If the metal that's trying to do the bumping out here is higher on this series than the one it's trying to bump out, then a reaction will occur. However, if the metal that's on the outside here or here is trying to bump out something here that's higher up, then no reaction happens. So using this series, which of these two reactions will not occur? Well, if I look at where iron is on this list, I can find it right here. It's kind of in the middle. Now, relative to it, it is trying to bump out copper. Well, copper is way down on the list. It's right down here. So because iron is larger, higher up than copper, it will in fact bump it out. So iron can take its place, copper can come out to be elemental copper as a solid, and iron will take its place, as we said. Now, if you're not told which valence of iron will be used, then you're going to choose the one that is the most popular. In the case of iron, iron 3 plus is the more popular ion, which you can determine from your alchem table. And so iron 3 plus would combine with that sulfate, and they would end up combining in a 2 to 3 ratio. And we can then go ahead and balance the equation. But that's not the focus of what I want to talk about here. I just want to show you how the transformation occurs from reactants to products. So in the second reaction, if we look where silver is located, silver is way down the list, way down here. And the only thing it can bump out is gold. Well, since calcium is in this ionic compound and calcium's way up high up here, there's no way silver can bump out calcium because calcium is higher in the poker hand, if you will, than silver is. And so to show that this bumping would not occur, or if it did, it would be incredibly, incredibly slow, we just simply have to write no reaction occurs. It's that simple. Right, so we now know about the activity series for metals. What about the bumping for nonmetals? Our focus for the nonmetals will be solely on the halogens, on the group 7 elements. And in this case, it's actually a very easy one to remember because fluorine is the strongest, followed by chlorine, and then bromine, then iodine, which also happens to correspond quite nicely with their order on the periodic table. And already, you know, fluorine is at the top and iodine's at the bottom. So it's very easy to see that this one is the strongest one for fluorine and that iodine is the weakest one. Okay. Let's take a look quickly at how this works. Fluorine can react with hydrochloric acid to make chlorine and hydrogen fluoride is the word equation. If you'd like to pause the video and try and do a structural equation or a chemical equation, you most certainly could, and then check this out. Now we have to remember when we're working with these group 7s that when they're elements, they're always diatomics. So the chemical equation would be F2 for fluorine, HCl for hydrochloric acid, Cl2 for chlorine, and HF. And so again, if we look at this time at sort of the non-metal bumping ability, the question is, can fluorine bump out chlorine? And the answer, of course, is yes, it can, because it's higher on the activity series of nonmetals than chlorine is. So it goes in and it needs to gain some electrons in order to become negative to bond with that H plus, and chlorine, on the other hand, will be the one that loses electrons so that it can become neutral and go out into fluorine spot. And that's how the substitution would occur. We can then go balance the equation quite easily. We can have 2 hydrochlorides here and 2 HFs here to make sure that all is well. To summarize, you can tell single displacement reactions by the types of elements they have on the left side and the right side, and the fact there's an element and a compound and an element and a compound.